Hello, how are you doing? I hope you're keeping safe. I sincerely do miss you. We would have been in class doing this, but hey, we have to be pragmatic. We have to stay safe. So here I am. I thought this would have come up yesterday, but I had few technical glitches. So let's do it. I do sincerely hope that you've had a look probably at the slides on Moodle. So I'm just taking you through that. You've got these slides and everything in here is quite important, right? This week, we have to think about a few other metrics of bonds and the ones which are very crucial when we need to think about including bonds into our portfolios. Okay, so the key concepts revolve around the duration of a bond and the modified duration and the convexity. So let's focus on that. And I think this slide here captures the essence of what you need to know, remember, and utilize in your professional life as far as bonds are concerned. So this diagram here pictures that basic relationship that we know exists between the price of a bond and the yield to maturity. So if you remember, we've always said that the yield to maturity is inversely related to the price. Effectively, there's a negative relationship. Okay, so as the yield increases, the bond price reduces. Or alternatively, as you reduce the yield, the price goes up. Why? Because remember, the price of the bond is the present value of the future cash flows. And because we are discounting using the yield, if the yield is bigger, the price gets smaller. But the most crucial thing that we are thinking about this week is what is the nature of that relationship between the price and the yield? How sensitive is the price to changes in the yield? Effectively, if the yield changes by a certain percentage, by how much does the price change? Okay, so what we need to do is we need to have metrics that measure these sensitivities. And the basic measure of sensitivity that you know of already is probably the duration. Right? If you remember the duration, so the duration effectively is captured by this black line here. It assumes that there is a linear relationship between the yield and the price. So you can see it's a straight line. Okay. However, we know that that is a very basic way to capture that relationship. The better way of capturing that relationship is through the convexity. So the convexity shows that, of course, there is a negative relationship, but the rate of change doesn't sit on a linear line like that. So you can see that the blue line there shows that there is kind of a non-linear, it's a curvature in the relationship. Okay, so what we'll be doing, the activities that we'll be doing in a minute, would basically start up with how to calculate the basic duration, sometimes also called the modified or Macaulay duration, and then to adapt or improve that in measuring the convexity. Then we would apply both metrics to changes in the yield to check to see the difference between the predictions of duration and the predictions of the convexity. So I hope that helps you, right? So don't worry about these complex formulae yet. Of course, you need to know how to use them, but I would show you. The essence of this week is please make sure that when you read, when you research, when you think about what you're learning for portfolio management this week, you're thinking about, can I calculate the modified duration? Can I use that to predict the direction of change in the price? Can I calculate the convexity, which is an adaptation or an add-on to the modified duration? And how does that lead to better predictions in the changes in the price when the yield changes. So what I'm going to do now is I'm just going to take you through this spreadsheet here, which I have put on Moodle, which essentially captures everything that we need to know. Basically, you can see we have a bond here. It's got a par value of 100, a coupon of 4%, and a yield of 5. From the term column here, you can work out that the bond has a 5-year life. Okay. Can you also please spot that there are cash flow coupon payments which are probably semi-annual? Can you work out why? Yeah, because we start from 0.5 and we jump to 1, 1.5, 2, 2.5, 3, 3.5, all the way through to 5. Bonds typically pay semi-annual interest. Of course, some bonds pay annual interest. So yeah, we've captured the terms there. And then we calculate the coupon payment. And of course, the coupon payment is 4% multiplied by 100, because we are thinking about a par value of 100. And I'm dividing it by 2 because they are semi-annual. And that's why we're paying 2 each time all the way through to the end, where the principal is paid and the interest is paid as well. That's why we have 102. So to calculate the price of a bond, technically, do you remember what we have to do? We have to discount these cash flows to their present value using the yield to maturity. And that is precisely what the spreadsheet does. You can see we are discounting 2 by 1 plus the yield to maturity raised to the power negative time. What I would suggest is that as you watch these videos, you pause them and you reflect on what I'm saying, because I have to quickly go through it. But then of course, if you open the Excel sheet on your computer as well, and then you can, if maybe you're watching the video on your phone, you can also be repeating what I'm doing. Right, so as you can see, you can confirm that each of these cash flows have been discounted to their present value using the yield and the time. So the price of this bond will be 95.884, isn't it? That should be the price of that bond. But what we are trying to think about here is what happens if this yield changes, right? What would happen? You can see from our diagram here that if, for example, we were somewhere here, right? If the price was somewhere there, for small changes in the yield to maturity, the black line will probably give us the same prediction as the blue line. But what if you have a huge jump? For example, if you move from here to somewhere there, then you can see that the black line, which is the duration line, will predict that price, but then the blue line is predicting a different price. So for small, tiny changes to yield to maturity, the price wouldn't change much. But for bigger changes in yield to maturity, the actual price will be very different from what we predicted by the duration. Okay, so to work out that, we need to, be able to estimate both the duration and the convexity. Okay, so let's go on then and do that. I'll demonstrate that in a minute. So to calculate the convexity, to calculate the duration, I should say, the duration is a time-weighted average of the present values of the cash flows. Okay, so what we're doing there is we're kind of taking a time average, a weighted average of these present values by multiplying each of these cash flows by the time. Okay, so when we do that, as we can see all the way to the end, we keep multiplying the cash flow by the time and we sum them up. We have the sum of the time weighted present values. To calculate the duration, we would divide the sum of the time weighted present values by the price. And if we did that, we come up with a figure of 4.570. And this is the time, right? This is effectively the time it would take for all the cash flows to be equivalent to the price. You can see there that the duration of 4.5 is shorter than the term to maturity of 5 years. Okay, so we would use this duration in a minute to work out the percentage change in the price if the yield to maturity changes by a tiny amount. To finalize what you need to remember from this spreadsheet, we need to work out the convexity. The convexity technically is, if you like, the square of the time weighted average of the present values. So what we mean here is effectively we're taking the weighted average like we did for the time weighted average, but we're also multiplying it by the time again. We're squaring the time. And if you see the formula there, to calculate the convexity, we take the time squared. Okay? Right. So that's effectively what we're doing. We're squaring the time and then we're adding the time again. So if we did that, if we squared it all the way through to the end, let's just come here all the way through to the end, and then we added them up. So the sum of that, like we did when we were taking the time weighted average of the present values, that gives us that figure there. Okay, so to work out the convexity, again, according to that formula there, right, that is what I'm simply implementing here. We pick that total sum of the squared time weighted average of the present values of the cash flows, and we divide that by the price times 1 plus again 1 plus the yield to maturity squared, right? Because we're trying, as you can see there, I'm trying to take the present value, right? The present value squared of everything in that box there. Okay, so in Excel, what I've just tried to do here is I've implemented that formula, the sum of all these guys, which is the figure that we had there, right? We're effectively multiplying it by 1 over 1 plus the yield squared. Okay, and that is what I'm doing there. You can see I'm doing 1 plus the yield squared. Okay, and we are dividing that by p, right? So because I divided and squared by 2, I've got the price there up. Okay, so I've effectively implemented that. Well, the complexity of this shouldn't really confound you, because what we were doing is we would be given the luxury of using our machine here, right? So that investment that you made in the calculator will come a bit handy in a minute. So let's finalize that computation there. So now we have effectively got our convexity. So we've got an understanding of how to calculate the Macaulay duration or the modified duration, and how to calculate the convexity. And once we have those figures, then we shall be able to predict the change in the price, that number there, when the yield changes by a tiny amount. Okay, so whilst we're here, let me begin by talking you through how you use your BA2 Plus professional calculator in some of these computations. The first one that I would want to talk about is how you use it to calculate the modified duration. Your calculator calculates the modified duration And once you know the modified duration, you'll be able to adapt it into the Macaulay duration, which is what you find in here. Okay. So the first thing I want you to do, please, is pick your calculator. And if you switch it on, we'll try and show you mine, but it's going to be a bit tricky. So if you have a calculator, you need to set your calculator up and be able to pick dates and time, because dates and time, for example, the term to maturity, etc., are quite crucial when you're calculating present values and future values. So the first thing you do is to set the date format. Okay. To set the date format, press the second function and then press the dot, right? The dot there. So if you press that, on mine here, you can see December comes up. Press the arrow button on top here. Keep going. The next one is degree. Keep going. I have set mine up to show or display the dates according to the European standard, which would do day, month, and year. Okay. If yours come up as US, then you need to set it. And to set it, you have to press second function again and set. You can see when I press second function and set, the US comes up. I don't want the US because I don't like the way the dates are recorded there. I want to stick by day, month, and year. Therefore, I'll press second function and set again. And in my case, I will leave it at the euro. And you can see the numbers there are 31, 12, 1990. Right? So please do that. If you struggle, just pause the video and make sure that you've set it up to euro 31, 12, 90. That's it for now. So we've set it. And once we've set it, we will be able to calculate the duration without going through that amount of number crunching. That's what we don't want to do, right? We just want to save time. So yeah, now let's attempt the calculation of the duration of this bond that we've used in this example to make sure that the sums are similar to what we find here. All right. So what you do is, again, if you press second function and then you press the number 9, you can see on top of the number 9, you have the bond there. So you press second function and you press the number 9 afterwards. Then SDT will show up on your screen, and this is where you have to enter the date. All right, so you have to pick a starting date for the bond, and it could be any date. I suggest that you set your starting date to be the 1st of January, the year 2000, so that you can then consistently just add numbers to it. The way you enter dates here is, I'm just going to type it on the screen so that you can do the same. The way you type dates is you use 2 digits for the day, and then you put dot, and then you have 2 digits for the month and 2 digits for the year. So to get the 1st of January 2000, what do you think I have to do? I'll do 01.0100. So let's just do that. So do that on your tiny computer. Do that. So 01.0100. And then press enter. When you press enter, the date then comes up. SDT is 1/01/2000. Please confirm you've got that. Good. So we set the date, and then we press the downward arrow button, and then it asks for the coupon. We just have to punch the coupon in as a whole number. So in this example, we have 4%, don't we? So all we do is just press the number 4 and then press enter. And you can see then 4 shows up. And then we go down again. And now it's asking us to enter the maturity date. The maturity date is the number of years after the start date that we set. Okay, so in this example, our bond matures in 5 years. Remember, we set our date to be the 1st of January 2000. That means here we have to set the date to the 1st of January 05, isn't it? Let's do that. So we'll do 01.0105. And then again, we do enter. And then just confirm that the date that comes up is 1/01/05. Good. Then we go down. It's asking for the redemption value. Just leave the redemption value at par. Don't change anything. Likewise, don't think about the actual days. I mean, it's not relevant for this computation. And then go down, and then the number that comes up is 1/y. This is the method that the coupon is paid. So in this example, the coupon is paid semi-annually, remember? So because the coupon is paid semi-annually, we're not going to leave it at 1/y. 1/y is when the coupon is paid annually. Okay, so we need to change the figure here to semi-annual. If yours by default shows 2/y, that means it's all right, so you don't need to change it. But mine was at 1/y, which is we pay the coupon once. You want to change it to you pay the coupon twice. So to change that, you just press second function and set. Please press and make sure that you leave it at 2 divided by y. Right, so that is the means of paying the coupon. And then press the downward button again. Now you need to enter the yield. The yield in this example is 5. So we press the number 5, and then we press enter. And then we're done, I think. We just go down. The price, we're not calculating the price now. So just leave that and press downward. And there is no accrued interest. Again, just press downward. And then you have the modified duration. So the modified duration is what I've entered there, is 4.4581. And you might say, oh, hang on, Charles, but that's not the same as the 4.570 that we had when we used the Excel. Yes, because the Excel calculated the Macaulay duration. And what your calculator does is your calculator always calculates the modified duration, which is brilliant, but it's not what you want here. If you want the two numbers to be the same, all you do is you just have to compound your modified duration by 1 unit of the yield. So all I mean is you multiply your modified duration by 1 plus the yield. Okay. Remember, the yield is 5%, but we pay interest or the coupon semi-annually. Therefore, we need to halve it. Okay, we need to halve the 5. That's why you can see here what I've done is I've multiplied the modified duration from my calculator by 1 plus 2.5%. And when I do that, bingo, right, the two numbers become equivalent. So what you've just done is fantastic. You've learned how to set your calculator up and how to use it to avoid all of that computation, right? All of that computation here by pressing the button on your calculator a few times. We're going to do other calculations. For now, I think it will be best to go to the problem-based learning activities, right? The PBL tasks here, and spend some time working through them. What I'm going to be doing is I'm going to take you through, I think, 2 of these tasks that are quite crucial. The rest, I think, when you read them, you will understand, right? Okay, so I'll take you to 3 of them, just 3. Have you had good reason to smile since you started watching the video? Give yourself a break, shake yourself up, and have fun. For now, let's come to question number 3. Question number 3, because that goes to the heart of the conversation that we've just had. So we have a 9-year bond with a yield of 15%. This time, see, we've given you the duration. And if the yield changes by 70 basis points, what will be the percentage change in the price? So remember, the whole idea of knowing about the duration and the convexity is so that you'll be able to predict the change in the price when the yield changes. Okay, so this question goes to the heart of it. The formula that will help us do that is to calculate the change in price. We would work that out by dividing the duration by 1 plus the yield multiplied by the change in the yield. So in this example, the duration is 8.908. The yield is 15%, so we are adding 1 plus 15% is 1.05. The change in the yield is 70 basis points. Basis points are units of 1%. Okay, so we will have to divide 7 by 1,000 to get the decimal value of your basis points. So yeah, and when you multiply that through, you can see there's a negative 0.0542. In percentage terms, what this is saying is, if the duration is 8.908 and the yield is 15%, then when the basis points changes by 70 basis points, the value of the bond will change by 5.42%. Of course, if the yield goes down, then the price will go up. And if the yield goes up, the price will go down. Did I say it well? Inverse relationship, isn't it? If the yield goes up, the price goes down. If the yield goes down, the price goes up. But the rate of change will be 5.42. Again, remember, this only works if the change is very tiny, because the blue and the black lines will be just about, basis points of 70 means it's less than 1%. So a tiny change, then that's fine. Okay, because the blue and the black lines are the same. But if the change was bigger, then what we're saying is what we've worked out using this formula would not be right, because the duration doesn't pick up the curvature, right? The change, the additional change. If I say it a bit mathematically, the duration is the first derivative, a derivative being the rate of change, and the convexity is the second derivative, right? So the convexity is the rate of change of the rate of change, and that captures the additional change. So we will work on that in a minute. But the basic thing now, I think, is probably clear that if we knew the duration, then we'll be able to work out the size or the magnitude and the direction of the change in the price. Good. Let's go on to the next example. Example number 4. It's a beautiful example. So in example number 4, we asked to find the duration of a 9% coupon bond making annual payments. That's very important. Remember, annual payment, because whether we have annual or semi-annual payments was going to have an impact on how we set up our calculator, isn't it? So let me just highlight that. If you're reading the question in the exam, you want to make sure you pick up the annual. And then there's a 3-year bond, and we have the yield to maturity of 9, and then we are going to be asked an additional question. What happens if the yield to maturity is 11.4%? So if we didn't have the calculator, then this is what we would have to do, right? We have to, like you saw in my Excel sheet, pick the time, state the cash flows, calculate the present value of each of these cash flows, add them up, and then do the time weighting, multiply that by the cash flow, right? Keep multiplying and dividing by the the total to find the weights, right? And then you do multiply the weight by, and then you add them up. Okay, so column 1 times column 4, column 1 times column 4, and then you add them up. So we would have been able to do that, but that is quite cumbersome, right? That's a long process. And that is why we invested in that. Okay, but remember, this gives you the modified duration. And once you know the modified duration, what do? You convert it into the Macaulay. Okay, good. So let's do that. So on your calculator, let me just do that as well. So what I'm doing is I'm going to second function and 9. I'm leaving the starting date on the 1st of Jan 2000. So I'm just pressing enter. I go down. The coupon, according to this question, is 9. So I change that to 9. I press enter. I go down again. The redemption date is 3 years. So I need to do 01.0103, enter. And that will set it to 1st of Jan 2003. Okay. And then I go down. I leave the redemption value. I leave the ACT. I need to change the type of interest payments from twice a year to once a year by doing second function set, enter, and I go down. The yield, I need to change that to 9%, enter, and I go down and down and down. My duration, according to this, is 2.5313, which is not the same as that. Well, but I know why. I know why, because that has calculated the modified duration, and the workings here is showing the Macaulay duration. So what do I have to do? I have to multiply my modified duration by 1 plus the yield, and the yield is 9% here. So I have to multiply this by 1.09, and that, my friends, give me 2.759. Thumbs up, which is the same as that. The question then goes on to say, find the duration of the bond in problem 4 if the coupons are paid semi-annually. Well, that's not too bad. No, sorry, you have to do the 11.4%. Sorry, what is the duration if the yield to maturity is 11.4? Can you imagine how cumbersome that would be if you didn't have the calculator? Then, as you can see in our answer here, you have to do the same workings again, changing your yield to 11.4. But because we have this guy, we can just go back. Right, we can just go back and change the figures. So let's just go back to second function and 9. We leave the date there. We go down. The coupon is the same. We leave it there. The date of redemption is the same. We leave it there. And then we go all the way to the yield. It's 11.4. Enter. And then the figure comes out as 2.4699. We know why. We know why it's not the same as 2.7514. Right? So we just have to multiply that by 1.114, because that's our yield to maturity, isn't it? And then enter, and then I think my calculator is saying 2.7514. Tell me if it is right. It is, isn't it? Good. So having a calculator is quite handy. And then, of course, I'm not going to go through the rest. The next one is saying find the duration of the bond if the coupons are paid semi-annually. All you need to do is go back into your calculator and change the type of interest payment from 1 over y to 2 over y. And then you're done. Because of time, this is getting longer. Let me take you down to question 7, which is so very, very crucial. Question 7 is so crucial because it summarizes everything that you need to know about bonds. It's so important, not just for us, for the exam or assessments, but at the highest level in practice, this activity summarizes how to price a bond, how to calculate the duration, how to use the convexity to predict changes in the price when the yield has changed, and to compare the duration results and the convexity results to see which one is the best. Okay. So all I'm going to do now is I'm just going to take you through two of the workings. I'll put the answers up on Moodle, and then when we catch up next week, we can see if you're able to get it done. So if you read this question carefully, you can see we've given you both the duration and the convexity, right? That's fine because you have enough workings to play with. So 30 years, wow. Can you imagine if you had to calculate the price of this 30-year bond yourself using your pen and paper in the exam? You will have interests that are stretching over 30 years, and it's going to be very cumbersome. You've got this. Okay, so 30-year bond, the coupon is 10.5%, duration is 14.23, convexity is 282, the bond is selling at yield to maturity of 5%. Why don't you work out what would happen if the yield to maturity falls to 4% or rises to 6%? Please notice that, we picked examples here where the change is not that big, right? And even when the change is not that big, we're expecting that the difference between the prediction of the duration and the prediction of the convexity will not be the same. Can you imagine if the change in yield to maturity is bigger, like probably we are experiencing now because of a crisis in the market? So what we will do now is, of course, you've got the answers here, but what I have also done is I've worked it out, I think, better to show you this in Excel. Okay, so use the Excel presentation here subsequently to really grasp the understanding. But otherwise, when we come back here, just to show you, what we need to do is we need to work out what the price of the bond will be given the data that we have. So it's a 30-year bond. The coupon is 10.5%. The yield to maturity now is 5%. Okay, so what will be the price of the bond? And then if the bond's yield to maturity changes to 4% and to 6%, what will be the prices as well? Again, without a calculator, working these things out by hand will be quite boring, frankly. So what we're going to do now is we just have the calculator. I'm just going to show you how to calculate one of the prices, and it's going to be the same all the time. So all you do is you just key in the data there. Okay, so let's start with the default. The default is what we know. We know we start with 5%, isn't it? That's where we are, and then the price changes when we go to 4%, and then the price changes again when we go to 6%. So let's start with 5%. So to work out the price for a yield to maturity of 5%, all you do is you do 30 and then N. Right, so I'm just keying that in, and then you do 105, and then you press on payment, and then you do 1,000 because it's a dollar bond, and that will be your future value. And then you do 5, which is your yield to maturity, and then you press compute. You can see compute there, the present value. So when you do that, the price comes up, it will show up as a negative figure because that's what you have to pay today to earn these cash flows. Right, so 1,845.48 there. You can do the same things for when the yield is 4% and when the yield is 6%. Just change the yield to 4% and 6%. When you do that, you get the prices. Okay, so you get the prices here. And the whole import of this question is, what happens when the yield to maturity goes down to 4%? And what happens if the yield to maturity goes down to 6%? Well, the question has given us the duration, and the question has also given us the convexity. Okay, so because the question has given us those figures, what we need to do now is we need to work out what the price will be, right? What the new price will be if we predict that value using either the duration or the convexity, right? So that's why I've used two different colors here. If you are predicting the change in price after the movement to 4% or 6% using the duration, then you're in the blue zone. If you're predicting the change in price after the yield to maturity has gone down to 4% or gone up to 6% using the convexity, then you'll be in the green zone, right? And we have the formula here. So these formula here are coming from your solutions from Moodle. That's kind of showing you how you worked out these new changes here, right? So if we just go through that, if you want to predict the change in price using duration, then this is the formula, right? It's the duration divided by 1 plus the yield to maturity times the change in price, of course, times the price. Right, the price, as we said, we start off with 5%, isn't it? So that will give us 250.11 if the yield goes up, right? If the yield goes up to 6%, that's the figure there. So if that is the case, then we are simply just adding. We're just adding this negative figure to that, which will give us a smaller value, right? So what we're saying is, now we know the real price is 1619, but if we had predicted this using the duration, that would have given us a prediction of 1595. So we need to work out the error rate. How accurate is our prediction using the duration? And in doing that, we compare this price with the truth. So what we're saying there is we're just looking at the difference between the two, and we're dividing it by the truth. So what we're saying is our duration prediction of the change in price is off by 1.485%. It's wrong by that magnitude. If we had to work out the change in price or the expected change in price using the convexity, right, then what we do is we have to use the formula, right? So the convexity formula, remember, just augments the duration. Okay, so you can see it here. That's the formula there. So if we implement it, then what we're saying is we pick the duration, we divide it by 1 plus the yield, multiplied by the basis change, but we need to add, according to the formula, half of the convexity and multiply by the square of the change. Remember, that's the second derivative. So it's the same thing here, but then we're squaring it here, okay? And then we multiply that by the price. That would have predicted a change of negative 222.04. Again, what we do is we add that to the truth, and that would have given us a prediction of 1621.44. Of course, it's not perfect. However, because it picks up the curvature, it gives us a smaller error if we compare the new or the predicted price with the truth. So the error that is given by the duration is bigger than the error that is given by the convexity, which kind of proves the fact that the black line and the blue line are not really the same. Even at smaller changes in the yield to maturity, there is a slight difference. And the fact that the convexity captures that curvature gives us a better prediction. Well, I didn't think this was going to be that long, but I think this essentially captures the good news that I had for you. And hope you've enjoyed this. Please work through your PBL activities, come up on Moodle and ask any questions. And I look forward to seeing you very soon. All the best.